Good morning or good afternoon, everyone. Thank you for joining the Terrestrial Ecosystems team meeting in conjunction with the Permafrost team. We have two speakers today, Erin Rooney and Kevin Schaefer. And Erin Rooney will start us off with her presentation. Erin is a research soil scientist for the U.S. Department of Agriculture, Natural Resources Conservation Services. And she's going to give us a presentation titled Leveraging Monitoring Networks and Field Method Development to Assess Variability in Landscapes Undergoing Permafrost Thaw. So with that, I'll turn it over to Erin. Thank you.
Awesome. Thank you so much. Let me get my screen shared. Okay. All right. I'm really excited to talk on this today. This is some of my favorite stuff to talk about. So really excited, appreciate the invitation to come talk with you all today. I am going to be talking about some of the work that we're doing at NRCS and some of the work that we're planning to do with taking monitoring networks and combining them with field method development to try to assess how variable some of these landscapes are that are undergoing permafrost thaw, and using that in some of our future products that soil survey is generating, like dynamic soil survey and mapping of these areas. There's a really exciting challenge of mapping these really complex soils in remote areas. There is a ton of spatial complexity. Right now, Alaska for soil survey is mapped at a very high order, kind of the highest one that we do. So there's a lot of different, a lot of space that is kind of grouped into a soil type, which is not to say that we're not doing a lot of really good work going to these remote areas. In fact, that's actually a key thing that I'm really excited about with NRCS is how much field data, how much soil data we're collecting. But there's a lot of space to cover in Alaska. There's also the temporal complexity of how these soils change sometimes year to year, which is then, we have to go back to the same places that we've been mapping and look again at those soils. And then there's some difficulties and challenges with our soil database. It's a very, very cool soil database, but it's not developed for permafrost soils. And so sometimes there are different important features that are relevant to permafrost landscapes that we don't have the ability to include in our soil descriptions in NASS. So things like permafrost depth, a lot of times we're just measuring the thaw depth when we're out there, whenever we're taking those soil profile descriptions. Different characteristics of the permafrost. So the permafrost temperature, the salinity, active versus relic permafrost. Some of these are recorded, but it can be a little bit different for everybody. And then associated features, if there's thermokarst, if there's different active layer detachments, thaw slumps, cryoturbation, all of these can be really hard to integrate into NASS. And then this all kind of leads us to this idea that permafrost affected soils require additional characterization so we can really capture these dynamic soil properties that will continue to change across time, and then also across sometimes very small amounts of space. So what we're thinking about a lot is what dynamic soil properties should we try to capture to best represent soil change. So if we have a 3D landscape where we have permafrost and we have changing permafrost topography, we have variation in organic layer thickness, we have seasonally changing redox conditions, we have surface features, canopy and vegetation kind of acting on these to create more variability. How do we capture that? What are the dynamic soil properties that are most important to represent spatially so that we can understand the variability associated with different soil types and try to use that to better map these systems and predict change in these systems? And then we also want to make sure that that data is scalable for future mapping efforts or modeling efforts. So what we're currently circling is taking the idea of the circumpolar active layer monitoring network grids that they have and trying to think of it as maybe a smaller version, a condensed version, but also with different measurements associated with a gridded system. So having GPS grids where we take thaw depth, distributed temperature profiles, organic layer thickness, estimate permafrost depth, look at subsidence, maybe document early season ponding. The idea being that we can kind of get this spatial variability across a grid without having to dig a bunch of soil pits, without having to take a bunch of soil cores. So ideally, we're trying to create something that would be a little bit less energy intensive. But we'll see if that's actually the case of how that method works out. And then also some associated measurements. So thinking about active layer redox, permafrost redox, and then permafrost ice richness. So these are some methods that we're kind of in the process of developing specifically for NRCS field staff. And our goal is to have some pilot testing of these at different sites in collaboration with some universities, with some other agencies like the Forest Service. And from here, we want to develop comprehensive descriptions of representative and transition soils. So using these methods to look at a soil, a representative soil, and then one that's undergoing disturbance, thaw, some sort of shift in saturation, a vegetation shift, and use that to test the appropriateness of the methods, and then also develop concepts to inform state and transition models that would ideally be applicable to other permafrost landscapes. So that's this method development piece where we're trying to link, we're trying to measure soil properties, but then we also want to link those soil properties with soil conditions. So ideally, we would be able to have this information about these gridded measurements, and then we could link that with continuous monitoring at specific sites to get a sense of this is how, in these types of soil conditions, in this soil climate, or also like the air climate, this is the variability that we see and the change in that variability with time. And so ideally, soil survey staff might be able to use this to revisit areas instead of redigging pits if it's a place they've been before, kind of tracking these key parameters to look at change and how that change is responding to these different soil climate factors. So we have some monitoring stations which we would use to get that continuous monitoring. We have some that are in collaboration with the Circumpolar Active Layer Monitoring Network. We have some that are in collaboration, or some that are just NRCS SCAN, Soil Climate Analysis Network sites. And then we're hoping to develop some with the Forest Service, some new hydroclimate monitoring networks. And ideally, we could also use these to calibrate. If we're working on developing a permafrost depth estimation method. And so this would help us to calibrate if that permafrost depth estimation, if that varies the accuracy of that method in different types of soils and different saturations at different latitudes, different vegetation covers. So to try to calibrate these methods as we develop them is also an important component so that we can make sure that we're delivering good data and recording good data. So from here, I'm going to shift into one of my favorite things to talk about, which is freeze thaw. Freeze thaw is a really important component. I'm sure I don't have to say that to this audience in these systems, and it is it complicates soil transformations. And there's a real challenge in developing cross-scale mechanistic understandings of how freeze thaw is changing the soil so that that information could be extrapolated to predicting change in soil. So to simplify that, it's difficult to predict where freeze thaw will occur, but if you do predict that, it's really difficult to predict how soil will respond to freeze thaw. So again, I probably don't really need to explain freeze thaw to this group, but it's a type of temperature-driven soil disturbance. It occurs across many ecosystems, and it can influence a range of soil properties. In the Arctic and permafrost environments, it drives cryogenic processes, which are a really key component of the structure, the hydrology, and the processes within these landscapes. Freeze thaw can have effects or play a role in frost heave, differential thaw, thermal cracking, cryogenic sorting. It can influence the organization of surface features and the subsurface, like cryoturbation. And so with it being such a key component of these landscapes, the question is, how will changing freeze thaw cycle frequency influence soils and things that we care about, like the soil organic carbon distribution and other characteristics of the soils? And I think one of the best figures that demonstrates the importance of this is this TULIC data from NRCS, where we see across 2 decades freeze-thaw cycle frequency increasing with depth, in a really nice visualization of this. We can also look at, and I should note, so that was NRCS. This is now NEON data, so that's why the TULIC it looks a little different. But we can look at how a latitudinal gradient shows a difference in freeze-thaw cycle frequency. So we can look at how freeze-thaw in the more southern sites is more frequent, and we can assume that maybe in those northern sites, as they become warmer, they might undergo more freeze-thaw. So drivers of freeze-thaw cycle frequency can help us with predicting where freeze-thaw is occurring. Just to skip forward because I'm running a little bit long. My friend Angela Possinger and I looked at different drivers of freeze-thaw across different seasons in cold and dry NEON sites, which were boreal and Arctic. We found that organic mat thickness played a strong role in driving freeze-thaw in the spring, less of a role in the fall. So we can kind of tease apart, this is what will drive freeze-thaw in different soils. This is where we expect to see it and why. But there's also modifiers of that freeze-thaw response. And those modifiers can influence the way that the soils respond to freeze-thaw. For example, saturation. This was an experiment where we saw that there were differences in how in the soils under canopy, open versus closed canopy. We saw differences in freeze-thaw cycles under open versus closed canopy. And those soil differences really disappeared when saturation began to play a stronger role at the foot slope. In another kind of view of this, when we had 2 soils, 2 permafrost soils, lower mineral that we put through experimental freeze-thaw cycles, we sort of expected similar responses because they had similar prior freeze-thaw history, but one of those soils was saturated, the Healy soil. And so again, saturation overshadowed the response of soil to freeze-thaw. And so we saw a different response to freeze-thaw from Healy than TULIC. So if you have 2 soils and you have freeze-thaw cycle frequency increasing down into the soils at the same depths, you can't expect those soils to respond the same way to freeze-thaw. Now we see freeze-thaw history overshadowing. Oh, am I going way too long? Do I need to wrap up? Okay, just cut me off.
No, you're fine on time.
Okay.
Yeah.
So here we see freeze-thaw history. So with the surface versus the active layer versus permafrost, we see totally different responses across 20 freeze-thaw cycles across those different depths. And this is in terms of the poorly crystalline iron fraction, where we see a different pattern of how that increases and then starts to decrease in a surface. We see a much faster increase and quicker decrease in active layer, and then very small shifts, if any, in the permafrost with the poorly crystalline iron fraction. This also raises the temporal complexity of freeze-thaw response, where if you have 5 freeze-thaw cycles 1 year, you might expect one reaction, but then in the subsequent years where more freeze-thaw occurs, you might see a change in the soil response. So that temporal complexity builds in another element of this response. And then this is where I'm wrapping up now. So with freeze-thaw, that temporal piece at the pore scale, we see after 5 freeze-thaw cycles in a permafrost aggregate, this decrease in the spatial connectivity of the pore network by quite a bit. We see connected water-filled pores in all of our permafrost aggregates decrease substantially, but this is a really striking image where we see that connectivity decrease following 5 freeze-thaw cycles. But in the literature, after 20 freeze-thaw cycles, we should really see a loosening, a more connectedness of the pore network. So this again shows that in those incipient freeze-thaw cycles, we might see one response of the soil that changes over time. So all of this to kind of lead to the idea that knowing that freeze-thaw is happening somewhere is not the same as knowing how freeze-thaw will affect the soils and how the physical, the mineral, the soil organic carbon dynamics of those soils will respond to freeze-thaw. And temporal is also a really important piece of this, where across time, that response can also change to freeze-thaw depending on how much freeze-thaw the soil has experienced up until that point. So that is my presentation that I organized for you all. This is a quick summary of what I spoke on, and then are we kind of holding for questions until the end?
Hi, Erin. Yeah, thanks for that. Great presentation. I really appreciate it. And I appreciate the questions at the very end. We will take a couple questions now, and then we'll leave a little bit of time after Kevin's talk to open it up for discussion. So why don't now I'll just open it up to see if anybody has a question before we introduce Kevin.
I see Vladimir Romanovsky with his hand up. Vlad, if
Okay,
you want
great.
to unmute and ask your question.
Yeah. Hi, Elizabeth. Erin, that's I have a question about terminology. Can you please say what do you mean by freeze thaw frequency? Are you talking about in one particular year? How many times soil freezes and thaws?
Oh, yes, thank you. That is an important clarification. Yeah, we're usually measuring that across the year, although sometimes we'll break it up into seasonally. But when I'm showing most of these figures, yeah, those were all annual, the frequency of freeze thaw across 1 year.
So how many times material freezes and thaws in 1 year, right?
Yes, yeah. We have different parameters depending on what we see in the data, but we usually try to give it a little bit of a buffer. So it's not right at 0 degrees Celsius. We'll go like +1, sorry, +1 or -1, and then it needs to be prolonged. There isn't like an official definition, right? But we want to get a sense that the soil has really fully frozen and fully thawed. So we'll have parameters built into the freeze thaw quantification package from Boswell et al. 2020 that will determine how long the soil has been above and below certain threshold.
At some particular depth, yeah.
Yep.
Mm-hmm. All right, but what I think that deeper in the active layer, it's usually happened just once a year, I believe. So the freeze and thaw during this thaw period of summertime, it could happen only in the very upper layers, right?
Yes, I think that as we see the permafrost thaw happen, that would be the main driver of deeper freeze thaw cycle frequency. That should be the main driver. That's not really what that one figure showed. I don't know exactly why that freeze thaw was increasing at that depth. Sorry, what were you going to say?
I'm not sure if it's real.
Oh, okay.
Well, yeah, because if you go deeper, usually deeper than 30 centimeters, you don't have really frequent freeze and thaw. It's just only one thaw and one freeze per year, usually.
Yeah, it's tough because in the temperature measurements we do see fluctuations, but it's there should probably be more. It's difficult to make sure that what we're seeing with those temperature fluctuations, we're not picking up an artifact.
Mm-hmm. Okay, thank you very much. Very nice presentation.
Thank you.
I see a question from Ryan. I guess we'll take your question, Ryan, and then we'll probably do Kevin's talk and then have an extended time at the end.
Great, thanks, Erin. Great presentation, really interesting. So hey, when you are talking about poor connectivity, is that three-dimensional, or is it just vertical?
Sorry, what was the last word that you said? Three-dimensional or what?
Or just vertical?
So that was three-dimensional. So in terms of how we determine poor connectivity in that experiment, that was the so we have unconnected water-filled pores, unconnected air-filled pores. So those are the paler numbers, or the paler colors, sorry. And so in terms of where that connectivity, yeah, that's kind of like an in the weeds. It's deceptively an in the weeds question in terms of like across which plane, across the the largest connected pore extent across any plane, Z, X, or Y. We had the most connected pore volume. We determined that to be the connected pore network, and then any that were disconnected from that in the 3D, spatially, those were now disconnected. Does that make sense?
Sure. Yeah. Okay. Yeah. Great. We'll move on. I'll read the paper. Thank you very much.
Yeah.
All right, Erin, thank you so much for your presentation and answering some questions. We'll have some more time after Kevin's talk. If there are some additional questions for Erin, we'll open it up to a Q&A session.
All right, and hi, this is Liz Hoy. I'm one of the other co-leads for the Terrestrial Ecosystems team, and I'm here to introduce Kevin Schaefer of the National Snow and Ice Data Center at the University of Colorado to talk with us about advances in remote sensing of permafrost dynamics. And thanks for joining us today, Kevin, and we'll let you take it away.
Thank you very much. Today I'm going to talk about the Permafrost Dynamics Observatory and how we're using radar to study permafrost dynamics. The Permafrost Dynamics Observatory is part of the above field campaign from NASA. Okay, it's not advancing now. I'm not sure why. Oh, there we go. Radar is trying to take advantage of the physical property that water expands when it freezes. And to get an idea of what this means, during the winter when the soil is frozen solid, it just stays steady. But when summer starts and the thawing starts, the ice turns into water and the soil gets smaller in depth. So you see a decrease in the height of the surface. When refreezing starts, when freezing starts in the fall again, the water in the soil changes back to ice and the ground heaves up, and this produces a seasonal subsidence. And what radar is trying to do, what you want to do with radar is you take two scenes at two different times, like the beginning of the thaw season and the end of the thaw season. You take the difference and you can actually measure that seasonal subsidence. And we've seen seasonal subsidence ranging from 1 to 5 centimeters. You could also look at long-term subsidence. Long-term thaw means that water is permanently changed back to water from ice, and you can then see a long-term subsidence trend. And this would include subsidence due to the draining of water, thermal karst, and you could also pick up even bigger subsidence due to erosion, often associated with thermal karst. What we did in the Permafrost Dynamics Observatory is we used L-band INSAR from aircraft, and we combined it with P-band backscatter, both radars, different wavelengths. And what we did is combined these two signals to estimate seasonal subsidence, active layer thickness, volumetric water content within the soil, water table depth, and then of course uncertainties for each of these estimated parameters. To give you a little bit of history of this, the idea for doing this kind of thing came when we were in Toolik Lake. We had just finished a hard week of drilling permafrost cores up on the north slope, and we were resting from the mosquitoes inside one of the huts and started talking about radar. And we thought, well, we could probably measure the seasonal subsidence. And it turns out we could. We developed an algorithm called RESALT. And starting in 2017, we got some grants funded, and then starting in 2017, NASA funded us, and we started using aircraft data. We published about 28 papers. We got a couple more in prep right now. 23 of those papers are actually for the above field campaign itself, and we have 10 data sets, 7 of which are now located at Oak Ridge National Lab, and you could look at the others. Are located in other places, other archives. These are all the swaths that we actually covered. These are all the aircraft swaths from the field campaign. This is all for 2017. And again, they flew in the beginning of the summer and they flew at the end of the summer. And we calculated all those parameters for each of these flights. There's 66 flight lines here. About 120 million data points overall. And at the bottom there is a DOI number. If you're interested, take a look at the data. I encourage you to go check it out. Now, what is it you can actually see with this kind of data? Now, if we can measure seasonal subsidence, and from that, if you make an assumption about the vertical distribution of water within the soil column, then you can actually estimate active layer thickness. And here you've got active layer, thaw depth on the Mackenzie Delta on the north slope or the north coast of Canada. If you look at long-term subsidence trends, you can get a measure of thermal karst activity. And in this case, we didn't use the aircraft data, we used satellite data to calculate long-term trends. But what we have here is a picture of a typical thermal karst on the north slope of Alaska. And on the bottom is a map of subsidence trends for a specific thermal karst feature near Dead Horse, Alaska. And the feature comes straight out. We actually surveyed this, and it pops out in the radar as really high subsidence rates. But there's more to it. When you take two radar scenes and try to take the difference between them, you want the scenes to be coherent. And what that really means, boils down to, is you want the scattering characteristics of the surface to be as close to each other as possible, so you're actually measuring a true difference in height. But when you have a fire, you burn off the surface, and it totally changes the scattering characteristics, and as a result, the coherence takes a big drop. And this is a picture here showing the Anaktuvik fire on the north slope of Alaska, and you can clearly see within the fire zone itself a big drop in coherence. There's also, basic backscattering, and radar penetrates the soil. Unlike visible wavelengths, which just reflect off the surface, it can penetrate into the soil, and how deep it penetrates depends entirely on how much soil moisture there is. And so you can take advantage of that to actually estimate soil moistures. And here's a picture near some wetlands near Old Crow Flats in Canada. Now, some more specific examples of processes that you may want to study. These are, impacts of fire on permafrost. In the upper right, you can see a pink dot showing where this swath actually is. It's in the YK Delta, and fires in 2009 or 2000. Well, I can't remember when. Sorry about that. But anyway, when a fire happens, the 2015 fire, sorry, and you can clearly see burned and unburned areas here. And what you see is that, in the burned areas, you see deeper active layers in wetter soils. And this is consistent with what people have seen with in situ measurements, but now we can measure it for the entire area, for the entire fire zone. You can also look at fire recovery. Now here we're looking at satellite data, so we want to look at long-term trends. And what you see here on the left is a picture of long-term trends in subsidence. You can clearly see the fire zones here. And in fact, I want to overlay the fire zones, and you can see that the different ages have different trends, some positive, some negative. And from that, you can actually do some space for time swaps and estimate how long does it take to recover. And we found that the active layer itself can recover to pre-fire values in about 15 years. However, in this area, this isn't the discontinuous zone. What we're seeing is that the thickness of the permafrost layer itself takes much longer to recover, up to 65 years. You can also look at long-term trends. Again, this is satellite data, but this is showing long-term subsidence trends on the north slope of Alaska. And you can see, the riverbeds are the blue lines that go up and down, vertical lines, and they show sometimes getting, heaving up, sometimes subsiding, very typical for these kind of riverbeds. But everywhere else in the tundra, what you see is long-term subsidence trends, which means it's thawing out and the ground is slowly subsiding. Now, the interesting exception is the black star right in the middle. That's Prudhoe Bay, and that's where they're doing all the drilling for oil, have been for the last few decades. And what they do is they inject seawater into the ground to push the oil up. And so you see here, it's all blue because the ground is heaving up as they pump the water in to get the oil out. Oh yeah, some labels. Now you can also take the data that we've been collecting, millions of data points, try to do a big picture data analysis. And we've been doing that. And what we see is, you know, a picture like this. This is actually a histogram, and the colors indicate, you know, the log base 10 of the number of points. So there's hundreds of millions of points here. But what we're seeing is that as the active layer gets deeper, the water table also gets deeper, which means that, you know, as the active layer goes down, so does the water table goes with it. That kind of makes sense. But the interesting thing is that what it also means is that even if the rain doesn't change, as the water table goes deeper and deeper, the surface soils can look a little bit drier. And so this adds an interesting wrinkle to the whole debate. You know, in the future, will the Arctic get wet or will it get dry? And here we're thinking if it starts thawing out, the surface soils will get drier, even if the precipitation doesn't change at all. Oh, and I had to put this picture in because the graph reminded me of the wave. Now, there's also an area that, you know, I think we really need to pay attention to, and this can really help, is the monitoring of infrastructure. A lot of people have built infrastructure that everyone depends on, and thawing permafrost is a big threat. And so far, all we could do is wait for the permafrost to thaw, the road to collapse, and then we go and rebuild it. And what I'm hoping to do is we could use this to, you know, perhaps give some advanced warning so that engineers can do something about it. This is near South Kalani Lake. You can see Silver City there. And, you know, infrastructure, typical, a runway, a road, there's a mine here. What we have here is seasonal subsidence on the right. And you can see, you know, most of the place seasonal subsidence is, 2 to 3 centimeters, except there are some places where the seasonal subsidence shows up as big red dots, much 3 to 4 times what's around the surrounding tundra. And this is actually an indication of thermokarst activity. And, for example, the thermokarst activity near the runway, there's some thermokarst ponds are forming. So but this could tell you, all right, is the runway at risk? Should we do some drainage out there to stop this? You know, at the mine on the right, is that normal mining activity, or is that a water holding berm about to collapse? And so these are things to look at. And on the lower left, large thermokarst activity that you can't even see in the visible images approaching the road. Is that going to damage the road? Can we do something to prevent it? So the hope is that this kind of information can provide tools to engineers to evaluate threats to infrastructure and perhaps hopefully do something before the infrastructure collapses. Now, in conclusion, we find that the synthetic aperture radar in general, is a really valuable tool to study a variety of permafrost processes. And we're looking forward to the launch of NISAR, which is the next U.S. radar satellite. And it should provide a huge amount of data like this that we can analyze. Thank you very much. I'm open to any questions. Oh, and by the way, this is after a tough field season doing surveys. This is the very end, last survey. We were very happy to be done.
That's a great picture. Thanks very much, Kevin. I wonder if we have any questions. We'll just take a few just for Kevin, and then we'll kind of open it up and have a larger discussion. Yeah, Vladimir, go ahead.
Sure. Kevin, good presentation. So in the very beginning of your presentation, you showed this kind of dynamic of subsidence and then heave when it's freezing. And rightly you showed that in the very beginning of the thawing season, subsidence rapidly going down. So how sensitive your method to the timing of the taking the measurements for your INSAR
I totally get you're saying. It's actually pretty sensitive. And what we do, ideally what you want to do is you get that measurement right after snowmelt when the thawing starts. That rarely happens. So what we did is we went to reanalysis temperature data. and created that square root of degree days curve, that curve that I showed. In fact, hang on, I'll go back to that. We use square root of degree days to come up with the shape of this curve. And then, you know, if we made the measurement here where my cursor is, we could adjust the seasonal amplitude to account for the fact that, you know, to try to hit this curve. We found it by doing that, we greatly increased the validation or the accuracy during our validation cycles.
Thank you.
Other questions specific to Kevin's talk? All right, well, then maybe we can have a bit more broad discussion with both of our speakers. And I want to thank both of them again for being here and participating. I'll just start off with a question that I wondered about, which was, you know, is there a way to kind of integrate some of the type of work that Erin talked about, this like mapping or monitoring permafrost on the ground with the type of airborne and satellite measurements that we'll have with the airborne emissions we've had from Kevin and the ones that we'll soon have with NISAR. I think, Kevin, you might even use some of the stations that Erin mentioned. I wanted to kind of talk about that a little bit. Yeah, Kevin, I see your hands up. Go ahead.
I think there, you know, Erin, was a great presentation. I thought it was really interesting. And Liz, I do think there's a lot of overlap because the work we're doing, we make an assumption about the porosity, the soil characteristics, the soil moisture in order to get the active layer thickness. And if we had better models of that, especially I like that porosity about the freeze thawing, that was really interesting. If we could get better data, more data, we can develop better models and adjust those models for different circumstances. For example, a pure peat bed versus a typical open tundra. So yeah, there's definitely overlap.
I don't know, Erin, if you wanted to comment on that too.
Yeah, that was a great response, Kevin. And yeah, I really loved your presentation. That was really interesting and exciting. I think that for me, the soil moisture piece of that, you know, whether the soils will be drier, will be wetter, that is really important information that would inform soil survey going forward. So having that data, like we can feed that data, and then that data can also feed our soil survey efforts and understanding of how the type of resolution we should be trying to get on the ground as well, which can be really helpful.
And yeah, Vladimir, go ahead.
Yeah, it's for both presenters. So yeah, as we know that the variability, the special variability of properties in permafrost regions very, very high, and if you have some point measurements of soils, how you upscale it to the you know, bigger maps. If in both of your work you rely on well, some sort of ecotype map, what Tor Jorgensen and colleagues developing, because it's actually probably the way to go to move from point point data in a soil characteristic case and properties in case of remote sensing using for active layer depth. You have to, you know, take into account your different soil structure, moisture, whatever. And I think this approach of ecotype approach will be very helpful to make your interpretation much better, and then eventually justify upscaling for the larger area and building maps.
For our retrievals, we did use ecosystem type in our retrievals. I'm not sure, I can't remember the exact name of the source, but I'm not sure it's the same one you mentioned. And we used a different one for Canada. But we recognize the large variability.
What I'm really saying, it's not just for, you know, big area, just along the swath, one swath. It's cover at least, you know, 5-10 ecotypes. And
yes,
do you do
know
differently for each ecotype? Do interpretation of your data a little bit different for different ecotypes within the one swath?
Yes, it is a little different. I think there's a lot of area of improvement, however, in how we do that, but we do it slightly different for each different ecotype. And in terms of the spatial variability, one thing we did do is for validation data, we developed long linear surveys where we repeatedly measured active layer thickness and soil moisture on and on, so that we could get as many pixels as covered as possible. And we tried to get good statistical averages within each pixel of in situ measurements that we can compare to the remote sensing data. I'll hand it off to Erin.
Thanks. Yeah, with our plans in Alaska, we're working to connect a lot of these observations and a lot of these measurements with ecological site descriptions, which I think would kind of be maybe a finer resolution than some of the ecotypes, or actually probably pretty similar to the ones that you were describing. I think you were talking about Jurgensen ecotype. So
about 15-30 meters resolution. Yeah. Mm-hmm.
Yeah. So probably very similar. Actually, those might be finer resolution than some of our ecological site descriptions. But yeah, there's in terms of the ultimate product that we want to have with dynamic soil survey, we don't know what that is going to look like throughout the whole US. And so there's a lot of opportunity right now to frame things in terms of ecological site descriptions in Alaska, to think about what permafrost specific properties we can bring in and make sure being measured and accounted for. I feel like I'm kind of going off the rails, but yes, I think that thinking about things and attaching them to ecotypes and for us ecological site descriptions is a really important path for this work.
Thank you.
Well, I had another question for both of you, and that was, I think Kevin put a little bit of this in his talk already. I wanted to ask a little bit about data availability and where people could find these data sets and how they could be accessed. And I know Kevin kind of mentioned some of that in his talking about many of these data sets are archived or published at what we call at NASA, these DACs, these active archive centers, and you can go and look them up and find them. I don't know, I might have missed it, Erin, if you mentioned a little bit about where can people find some of the data sets that you've worked on and worked with. I know neon data, I know where to find that, but
so in terms of the freeze thaw data sets, those are all available through the papers. Everything is open in like GitHub repositories. The NRCS specific data, so all of that it has to be publicly available. There's a couple issues that we're working out in terms of having whether it's like daily averages or if it's hourly averages for some of the soil climate analysis network. No, so that's a scan, sorry, for some of the calm associated stations, but all of that should be held in public repositories. We're still figuring some stuff out for data that doesn't currently exist, like for our Forest Service collaborations. That's something that we're developing kind of partnership wide in terms of where that will be publicly available. So it will be, but I can't say where yet. And then of course, for all of the soil data, that's available in Web Soil Survey. It's also available on Soil Web. And both are very fun applications to peruse. And so hopefully as we continue getting Alaska, the initial mapping done, more of that data in Soil Web and Web Soil Survey will be populated, and people can browse that.
Yeah, I see. Well, Jeff, is your question related to this issue of data availability?
Yeah, actually it is. I just sort of have a comment as a practitioner who doesn't do this doesn't do permafrost full time. Sometimes it seems like the amount of data everybody wants more data, which is great, but the amount of data and where it's located can be really pretty problematic to track down. And I just thought I'd throw out for the discussion, if there was some kind of a comprehensive cheat sheet of where to find different data sets, that would be very useful for engineering folks who, I mean, Kevin, some of your stuff is great. And for highway infrastructure, airport infrastructure, we rarely look very far beyond our right of way because we have no jurisdiction beyond our right of way. But in the case of some of the thermal karting, especially some of the stuff that's happening in Canada, what's outside of your right of way enters your right of way before you know it. And knowing that's coming, frozen debris lobe on the Dalton Highway is another example of something where it was brought to our attention. Frankly, we kind of poo-pooed it until it got close enough to where we really recognized it as a hazard and recognized we had to do something about it.
Oh yeah, I totally get what you're talking about, Jeff. Just last summer we went up to the North Slope, and you could take radar, for example, and just monitor the road itself, but that's not really the clue. The clue is the giant thermal karst pond that's encroaching upon your road right next to it. And if you had some advanced warning that this pond is getting bigger and encroaching on a road, well, you could do something like you put a pipe in to drain the water out, or something like that. It gives you options, more options, I think, than wait until the road collapses and then we'll do something about it, which I think we can all agree is like the worst possible option. But in terms of data availability, I put in the chat a link to the aircraft data, and also in there is a validation data set, modeling data sets, whole bunch of data sets. Now, I do have a number of data sets from previous papers that we would like to consolidate and put at the DAC. Haven't had a lot of time, Liz, to do that, quite honestly. And I know Liz has someone updating our validation data set. So we're trying to do what you're saying, Jeff. And I would also say that we're hoping that with NISAR, we can make regular products that engineers like yourself can use to try to evaluate threats to infrastructure. That'd be really useful, I think.
yeah, that would be great. I'm actually having an interview with some of the Permafrost Discovery Gateway folks this afternoon to talk about their interface, and it makes me wonder if there was a potential for linking some of these data sets through that, or if there's some other portal that allows access to a lot of different things.
Are you talking with Matt Jones from that Permafrost Discovery Gateway? Or?
Anna and Ezio.
Yeah. Permafrost Discovery Gateway is designed to kind of be, I think, a little bit more outward facing and make use of some of these data sets. And it sounds like, I think they said they've have like 85 data sets in there right now. And it's just kind of a matter of how much time they have to ingest more data sets, because I brought up Kevin's data set to them and said this would be a good one to put in Permafrost Discovery Gateway. So maybe, Jeff, you can mention it to them too when you talk to them.
Yep, I'll give you a plug.
Yeah. Yeah, I think I'm really glad that you brought this up, Jeff, because I think this is something that happens. And in the fall, our team did a joint IARPIC call with the data team, the foundational data collaboration team of IARPIC, to talk about the fact that there are many different archive centers for Arctic data, and it can be difficult to kind of navigate all of them. They're all set up very nicely, but there's many of them. And so there's an idea to put data into this one kind of system called Data One, which I think some people are starting to think about. But I think it's something that IARPIC can think about too, is how do we kind of come together for the community and create this platform, or be a platform to kind of share some of these data sets. So I'm glad you brought it up. I took some notes down because I think it's worth pursuing for IARPIC too.
Great, thank you.
Yeah, Mark says we need a data set of data sets, and it's very true. All right. Any last questions that people want to bring up? If not, we have Tony is going to give a little plug to talk about the next implementation plan that IARPIC is starting. We just want to take like 5 minutes here at the end and do that. So I want to make sure we have time for her to do that. So I really appreciate our discussion we've had, and I think I'll turn it back over to Tony and let her talk a little bit about the next implementation plan.
Perfect. Thank you, Liz. And yes, just want to echo thanks to Erin and Kevin for being here today and for your presentations, and for everybody for joining. Like Liz said, just wanted to take a couple minutes while I have got folks to remind everyone, or to bring your awareness if you're not already aware, that we're in the process right now of updating our biennial implementation plan. So that will outline team and communities of practice like terrestrial ecosystems, like what their objectives and deliverables are for the next 2 years. So I'm gonna pop a link into the chat and then share my screen just to bring up a visual slide of this information. But either using that link in the chat or using, here we go, the QR code on the slide that should be on everyone's screens right now, you can access a form with a little bit more information about the Arctic Research Plan and then the 2-year biennial implementation plans that support that broader research plan. So again, like I said, we are currently in the open public engagement period for input and feedback on the current plan. So that's March through the end of May. We are just looking for anybody in the community to give us input, feedback on any deliverables from the current plan that we're working towards that should be continued, maybe with some adjustments, any that we think should be closed out, maybe they've been completed, maybe priorities have shifted and there's other things we need to be focusing on, or if there's anything completely new that's not in this plan that should be added. You know, it won't be a complete rewrite of the plan, but we just want to make sure that we adjust any deliverables, make any additions, changes, so that we still feel like as a community we're headed in the right direction. So again, link in the chat, QR code will take you to a Google form where it'll have links to the current plan, so you can take a look, and then it'll have areas where you can answer any of these questions on, you know, what your thoughts are on what should be continued, closed out, and added.
And I'll just second this and say every comment is looked at and addressed by the IARPIC team. And so, you know, you really can, as a community, think about what's important and where you want the IARPIC to focus. So really consider putting in some comments. They're all looked at and addressed. And all right, well, thank you all very much, Erin and Kevin. Thank you again for talking. Next month, we'll have a series, or we'll have a few presentations about fire in the Arctic and Boreal regions, kind of talking about wildland fire. So we'll send out some information about that soon. So that'll be, it's the third Thursday at 2 p.m. Eastern. So I believe that is it's going to be the 18th of April at 2 p.m. Eastern. We'll have our next call about fire-related disturbance. So thank you all very much. Bye-bye.
Thank you, everyone.
Thank you.
Great. Thanks, Tony.
Thank you, Liz.
See ya.